Hello students. This problem, we're going to compute this integral over this region, which is a little square, but it's tilted, and it has these corners. So in order to compute this integral, we're going to transform to another coordinate system. And in this coordinate system, we're going to compute this integral over a rectangle. So we'll need to find this transformation, and then recall for change of variables, we'll have to take the Jacobian of this transformation, as well as find the limits of integration, which will inevitably be the corners of this rectangle. So first we'll notice that x squared minus y squared is the product x minus y times x plus y, and once we know that, this gives us a potential transformation. So we're going to let u equal x minus y and v be x plus y. Now I wrote this twice, and you'll see why in a moment, because I'm going to need to devise the transformation. Once I have the transformation, we'll compute the Jacobian, and then once we have the Jacobian, we'll transform this integral, and then we'll use these definitions for u and v to determine the corners of the rectangle. So let's go ahead and do that. So if I add these two equations, u plus v is 2x, because the y's cancel, and then u minus v, the x's cancel, and we get minus y, and that gives us minus 2y. So if I solve for x, I simply get x is 1/2 u plus v, and I get y is minus 1/2 u minus v. So I'm going to take these coordinates and make them my coordinates for the transformation. And then once I have this transformation, I simply take its Jacobian. So I take the partial of the x coordinate with respect to u, I get a 1/2. The partial of the v coordinate with respect to u is minus 1/2. And similarly, the partial of the x coordinate with respect to v is 1/2, and the partial of the y coordinate with respect to v is minus 1/2, which is a plus 1/2. So when I take this determinant, we simply get 1/4 plus 1/4, which is 1/2. Now that I have the Jacobian, I'm going to go about finding the limits of integration, and you'll notice that this point here gets mapped to this point here, and you could tell that because if you have x is 1, y is 0, when x is 1 and y is 0, then u is 1 and v is 1. So 1, 0 gets mapped to 1, 1. Similarly, 0, comma 1, so when x is 0 and y is 1, the x's are zeros and the y's are 1, so that means u is minus 1 and v is 1. So we get mapped to minus 1, 1. And then similarly for the remaining coordinates, this point gets mapped to this one here, and the bottom of the little diamond here gets mapped to the bottom right corner of the rectangle. So this is going to allow me to set up my limits of integration. So you can see that u is between 1 and minus 1. I'll simply write that here. U is between 1 and minus 1, and then v is similarly between 1 and minus 1. So we get this square here in the uv coordinate system. Okay, and then the next thing we'll realize is that once again u is x minus y and v is x plus y. And we are ready to make our change of variables for our integral. So I'll integrate with respect to u first, and that means u is between minus 1 and 1, and then I'll integrate with respect to v, and v is between minus 1 and 1, and the Jacobian is 1/2, and x plus y is v, but x plus y squared means we have v squared, and then remember x squared minus y squared here is equal to u times v, so I have e to the uv. So now that I have this integral, I just simply integrate, and I'll just show you all the steps for that in one fell swoop. So I'll factor out the 1/2, and then if you just integrate this, when you integrate the exponential, remember that we're treating v as a constant, so we end up dividing by v. So what you have here is that one of these v's and one of these v's cancel, so you're left with this v here. And then I'm just going to let u be 1 and u be minus 1 and subtract them. That's fundamental theorem of calculus. And now you just have to set up this integral. But I split that into two pieces, so now it's in its two constitutive parts. And I'm going to do an integration by parts on each of these. So if I do integration by parts on this one, I get v e to the v, and then we're integrating from minus 1 to 1. We get a minus, and then we just have to integrate e to the v. Similarly, because we have a minus sign here, we're going to flip-flop these signs, and that's going to, we have to keep track of those signs, and then you just evaluate this expression at 1, and then you subtract that expression at minus 1, so you're going to get a plus there. And then similarly, you integrate this, you get e to the v again, and then you'll get e to the 1 minus e to the minus 1, but then you distribute the negative 1, and you flip-flop the signs, and then you get the e to the 1's cancel, and you have 2 e to the minus 1 divided by 2, which is e to the minus 1 for that section. And then you do this similarly, you do the evaluation here, and it works out that you get a minus 2 e to the minus 1, but then you multiply that by a minus 1/2, and you get an e to the minus 1. You add those together, and you get 2 e to the minus 1. And that is how you do the change of variables and complete the integration. All right, good luck.